So the next problem is talking about a bottle being filled with water. Let h of v represent the height of water in the vase. I guess it's really a bottle, so maybe we'll... Yeah, it's a bottle. In inches, and let v represent the volume of water in the bottle in fluid ounces, okay? Explain what the expression h of 56 minus h of 23 represents in the context. So the function h takes a volume and outputs the height, right? So this 56 here is a volume, and this 23 here is a volume. So when you input that volume into the function, you get out a height. So this is the change in height when volume changes from 23 fluid ounces to 56 fluid ounces. Explain what the solution to the equation h of v equals 4.7 represents in the context of this situation. So again, the function h inputs a volume and you get out a height. So this 4.7, this is a height in inches. And so what we want is the solution is the volume of water in the bottle when the height is 4.7 inches. So the next one says, explain what the equation h inverse of 7.5 equals 60.1 means in the context of this situation. So again, the h function takes an input of a volume and outputs a height. So h inverse inputs a height and outputs a volume. Okay, and so what this represents is that the volume is 60.1 fluid ounces when the height is 7.5 inches. Then it says, suppose the image below illustrates the bottle being filled with water. On the axes provided, sketch a graph of the height of the water of the bottle in inches as a function of the volume in fluid ounces. So here we're wanting to do height as a function of volume. So what that means is that height is going to be the output and volume is going to be the input, independent variable. So height is a function of volume. That means the volume is going to determine the height in this case. And so clearly when the volume is 0, the height is 0. So we know that 0, 0 is going to be on there. The other thing we can realize is that as we fill this up, as volume increases, the height will also increase. So as volume increases, the height is going to increase. And so the question of that, so we know we're going to have an increasing function here, but the question is, how does it increase? So what we can think about is if we set some amount of volume and we put a little bit in there, at first, for some fixed amount of volume, it'll fill up, kind of quickly. But as the bottle gets wider, some fixed amount of volume will spread out thin and it won't cause as much change in height. So you're going to have this kind of, where at first, changes in volume will affect changes in height a lot, and then it will kind of taper off as it gets wider. And when you get to this widest point, that will be the least steep place on the graph. So right here, maybe here, corresponds to the middle of the bottle. And then at that point, it starts doing the opposite thing. So again, when we fill this out, a fixed amount of volume will spread thin and won't cause very much change in the height. But as we go up and it gets thinner, it gets less wide, then a little change in volume will go further as far as making an increase in the height. So it's going to be concave up here. And then when we get to this point, we have this constant rate of change between volume and height because the width of the bottle is not changing. And so when we have a constant rate of change, that's going to be linear. So it's going to be kind of linear at this point on. So this is the top, where it's the neck, bottom of the neck of the bottle, and then the neck of the bottle, since it's a constant width, is going to be a constant rate of change there between volume and height. All right, for this one, we're going to reason graphically about these limits. So the first one says I want to find the limit as x approaches -4. And so when I'm looking at that, I'm looking as I'm going in up from the left and right to -4, what's happening with my y values? Well, from the left and right, it looks like they're approaching the same y value. And if I go over here to my y-axis here, I can see that my left and right hand limits are both approaching 6. So the two-sided limit here as x goes to -4 is 6. So the next one says I want to look at f of -3. So I'm going to go here to -3, and I'm going to go up, and I can see a closed dot right there, and that closed dot happens at y equals 4. So that's the there. The next question asks to find the limit as x approaches -3 from the left. So I'm coming in this way to -3. And what's happening to my y values? It looks like they're approaching 4. Then the next one asks for the limit as x approaches 5 from the right. And so I'm going to go over here to 5. And I want to come in from the right-hand side. And so the limit as x approaches 5 from the right, it looks like it's going towards the y value 12. The next question asks for the limit as x approaches -3 from the right. So if I approach -3 from the right, let me erase this other stuff around -3. So if I approach -3 from the right-hand side, so that's going this way on the x-axis, what's happening to my y values? My y values are going off to positive infinity. The next one is asking for the limit as x approaches 0. And so since it doesn't specify the left and right, that's a two-sided limit. So as I come in to 0 from the right-hand side, it looks like my y values are going down to -2. But as I come in towards 0 from the left-hand side, my y values are going to +2. So since my left and right-hand limits are not the same, we say this limit does not exist. The next question is asking for f of 5 minus f of 0. So f of 5 should be a value we can just find from the table. So if I go over here to 5 on the x-axis and I go up, I see that filled in dot happens at y equals 10. And f of 0, if I go over here to 0 and I go up on the x-axis, I see that filled in dot is at 2. So 10 minus 2 is 8. The next one might be a little bit hard to see because there's a lot going on there. But what it's saying is it wants to know this, this is an average rate of change of the function at x equal -4. And so that's just some average rate of change as this delta x goes to 0. So if you recognize that, that's the definition of derivative, right? And so we're looking for the derivative of the function when x equals -4. And if I go over here to where x equals -4, I can see that that portion of the graph is linear. And so all I need to do is compute that slope. And so I notice that if I go from the point -4, if I go backwards 1, I go up 2 units. And so the slope there is -2. Okay. And then, so that's just a rise over run. So I have 2 and then -1. So back 1, up 2. So just pay attention to the labels here because this goes from 6 to 8. But this -4 to -5 goes back 1. Okay, then the limit as x approaches 3 of f of x. So I go over here to 3, and I'm going to be coming in from both sides and seeing what's happening. As I come in from the right, I can see it's approaching 4, and from the left also 4. And so the two-sided limit there is 4. The next question says identify all the x values for which f is not continuous. And so one kind of maybe easy way to think about continuity is to think about when I don't, any place where I have to pick up my pencil as a discontinuity. So as I'm going along here, let's start at the far left-hand side of the graph. I'm just going to trace it. And I notice right here at x equal -3, I have to pick up my pencil, and I have this, this is an infinite discontinuity at x equal -3. Okay, so let's keep going. And the next discontinuity is a removable discontinuity. It just has a hole in the graph there at x equal -2. And I keep going, and it looks like at x equals 0, I have something called a jump discontinuity. So I jump there. And then at x equal 3, again, a removable discontinuity. And then come up here to x equal 5, I have another jump discontinuity. And that's it. The next question asks what's the domain of f. So that's all the possible inputs that have a defined output. And so as I'm looking along here, at -3 at this discontinuity, there is actually an input there. At -3, the function value is 4. So that one is not a problem. So I'm again looking at these places where I had a discontinuity, and I'm looking at is the function defined there. At x equal -2, I can see there is no defined function there. So x equals -2 is not in my domain. Again, at 0, my function is defined to be 2. At 3, my function is not defined at all. There's no solid dot there at x equal 3. At x equal 5, there is a solid dot. So the only places where my function is not defined are at -2 and at 3. So I can draw a number line here. And I want to leave out -2 and 3. And so if I leave those out and I shade everything else, I can see that my domain is in 3 pieces. And so I can write down those 3 pieces in interval notation by writing -infinity to -2, union, -2 to 3, union, 3 to infinity. And I think it helps sometimes to write down the picture of your number line before you write down interval notation. I just think it helps organize yourself. Okay, so for this one I have a function that's defined by this graph here. And so the first question, actually I'm going to do B first and then A. So this one says, is the function continuous at x equals 0? Use the definition of continuity at a point to justify your response. So to see if it's continuous at 0, I want to look at the left and right hand limits. So the limit as x approaches 0 from the right of f of x is equal to the limit as x approaches 0 from the right. Well, if I'm going from the right, which of these functions am I using? I'm going to be using this one as I'm coming in from the right, because, coming in from the right would be greater than 0. So that's this one. So I'm going to use that function. So 1 over x squared minus 25. And what I might notice is that this function is actually continuous at 0, so I can go ahead and plug in 0. So I get -1 over 25. If I look at the left-hand limit of my function f, my function f is defined for x less than 0 to be this function. So that's the one I'm going to use as I'm coming in from the left-hand side. And I might notice that if I plug in 0, I get something that's defined, so this function is actually continuous at 0. So I get -3 there. And what I notice is that my left and right hand limits are not equal. And so if my left and right hand limits are not equal, then my function is not continuous at 0. Okay. And then something I know about continuity and how it relates to differentiability is I know that if the function is not continuous, it's not differentiable. So not differentiable because the function is not continuous. At x equals 0. On number 5, it says we want to use the definition of derivative to prove that the derivative of 3x squared minus 4 is 6x. And so the definition of derivative is going to be the one that where we're going to take the average rate of change as the length of my interval of average rate of change shrinks to 0. And we want to show that that limit is equal to 6x. So here, let me set this up. So I'm going to use the limit as h goes to 0 of f of x plus h minus f of x over h. So that's the limit as h goes to 0 of, I'm going to take x plus h and plug it into my function. So 3x plus h squared minus 4 minus 3x squared minus 4. You've got to remember that we're subtracting that whole thing, so the parentheses goes around that, all over h. And so if I simplify that further, I'll get the limit as h goes to 0, and it's important to remember that limit each time you write another equal sign. Put that limit there, or the equality doesn't hold. When I do that, I get 3, and then if I square this x plus h, we know x plus h squared is equal to x plus h times x plus h, and if we multiply that, I get x squared plus xh plus xh plus h squared, which is x squared plus 2xh plus h squared. So that's what we're going to use for that. So 3x squared plus 2xh plus h squared minus 4, and then I'm going to go ahead and distribute this negative sign into both of these. And so I'm going to get minus 3x squared plus 4. All of that's over h. And so I'm going to continue this down. The limit as h goes to 0. I'm going to go ahead and distribute that 3 into each of these things. And so I'll have 3x squared plus 6xh plus 3h squared minus 3x squared plus 4. All of that's over h. And what I can see here is I have some common factors. I have the 3x squared and the minus 3x squared. And I have the, oh, whoops, I lost a 4 there. I should have had a minus 4 here. And so that minus 4 and that plus 4 add to 0. And so what am I left with on top? I just have the limit as h goes to 0 of 6xh minus 3h squared over h. And I'm feeling happy right now because I can see that in each of those factors on top I have an h. So what I'm going to do is I'm going to pull that h out of that. And when I do that, what's left over in this term? Just a 6x. And in this term, what's left is a minus 3h over h. And then I can notice that h over h, that divides to make 1. And so, so I don't have to write that term anymore. That's the limit as h goes to 0 of 6x plus, minus 3h. And then now I can go ahead and take that limit because this function, now that I got rid of that h in the denominator, this function is now continuous at 0. So I can go ahead and plug in 0 for h, and I'll get limit, or basically I'll get 6x minus 3 times 0, which is 6x.